for thinking about philosophy of cosmology. And I'm particularly interested there in just getting a kind of sort of more thorough picture of, structurally speaking, how the kind of branching processes in the Everett interpretation work, how decoherence is supposed to work here, how the transition between quantum and classical is going to work here. And in fact, a lot of what I'll say in that context is going to be relatively neutral on interpretations. A lot of it, in fact, is going to be looking at how, at least from the point of view of physical practice, we do the quantum mechanical version of a lot of the statistical mechanical material that David in particular talked us through in the first couple of days. Okay, so let me start with a warm-up. Let's go back to classical mechanics and look at how we go from the microscopic physics to claims about macroscopic dynamical principles in classical physics. And I think we can usefully, and here I'm going to be in some ways recapitulating what David's been saying, but from a slightly different spin, we can usefully distinguish three kinds of dynamics we do classically. So we have state dynamics, by which I mean the dynamics of individual phase space points. Probability dynamics, which is the dynamics of distributions, if you like, real normalized functions over phase space points. History dynamics. And what I mean by history dynamics is sequences of macro states of the system. So you remember from David's point of view, set up the presentation, if I have the phase space of a system, I can carve it into macro states. And when I can say of a given system, okay, at time t1, it was in macrostate I1, at time t1 plus delta t, it was in macrostate I2, at time t1 plus 2 delta t, it was in macrostate I2 again, and so on. And so the history dynamics represents the system at a given time by a macrostate and looks at the sequences of macrostates. And if we ask what the dynamics looks like here in classical mechanics, we've got sequence of dynamical principles, each one coming from the last. So for the state dynamics side, we've got the dynamics being represented by Hamilton's equations. So I should say I'm using a non-standard convention for this lecture, whereby the equal signs means equal up to a possible sign error. That's just the baseline dynamics we have in the state system. That induces a dynamics on probability distributions on phase space. Definitely a place where the sign error issue comes in. quantitative dynamics in a second. Let's just pause what we're doing there. The point is this: if I know how individual phase space points evolve, then I know how a probability distribution over phase space points evolve. Because I can say this little blob of phase space points right here, over some time t, it evolves to this little blob over here, and so given a distribution that tells me what fraction of the probability is to be put in each little blob, I now know what fraction of the probability is to be put in each little blob after the evolution. And so this thing is just a straightforward mathematical consequence of this thing. Who's seen that formula, just so I know? Yeah, that's good. Not everyone in it. Fine. And this system by itself, mathematically speaking, is a perfectly well-defined dynamical system. But of course, conceptually speaking, our understanding of it is very derivative on the first system. But in fact, in doing a lot of statistical mechanics, a lot of what we're in the business of doing, and this came up in some of the discussion in Tim's talk, is we're in the business of looking at the evolution of the functions and abstracting away from the evolution of the individual systems. There'd be no point doing that at all if what we wanted was the exact answers. Often what we want to know is only approximately how well this thing evolves, and then sometimes we can get to it direct. Why might we only want to know approximately how the probabilities evolve? Because we might be interested not in the exact evolution of the whole probability distribution, but what the probability is at any given time that the system's in a given macro state. So, suppose I've got a probability distribution rho at some time, and suppose I've got a macro state I, which is just some region of phase space. How do I work out the probability of that region? So I've got phase space is a macro state in phase space. Got a probability function of phase space. What's the probability the system's in here? Say again? Yeah, you just integrate over this set. So this set is I, then the probability of I is just going to be the integral restricted to I of rho. A quick bit of formalism. Let me write pi I is the functional that takes a function rho and it replaces it with the function that's unchanged inside the region I and is equal to 0 everywhere else, okay? So rho of x equals rho of x in x is in region I, 0 otherwise. Why is that useful? Because if I've got this defined, then the probability of I is just the integral over the whole space of pi I rho. When you think about pi I rho up to conditionalization, is the probability up to normalization is the probability distribution conditional on the system being in macro state I. Okay, so suppose I know how the probability distribution evolves, and I want to know what the probability is of a sequence of macro states. Here's how I do it. At some particular times, t1 plus delta t, t1 plus 2 delta t, and so on. So maybe the macro states, for instance, are characterized by the distribution of speeds in a gas in the way that Tim was telling us about, in which case I want to know what's the probability that the system at time t1 had this distribution, at time t1 plus delta t had another distribution, at time t1 plus 2 delta t had another distribution, and so on. Just mathematically for a minute. What that probability means, how to understand it, is a vexed question as we've seen, but just in terms of the mathematics for a minute, how do we do that? The answer is fairly straightforward again. I take my distribution rho, I restrict it to macro state I1, I evolve it forward, I restrict it to macro state I2, I evolve it forward again, I restrict again, I keep doing that. At the end of the whole process, I integrate out, and that gives me the probability of the whole system.
That would be the integral with a delta p over t added into it.
Say again?
that would be the integral over the whole phase space through delta p with delta p, the phase space symbol there, n over I. And it would be a double integral of I and t, wouldn't it? I mean, I representing the area of the little microscope, the region. Well, I may have it wrong. That's right.
Yeah, it's only one integral. Let me show you what it is. So just remind us that the method we use to get the probability of some macroscopic history is restrict, evolve, restrict, evolve, restrict, evolve, all the way up, and then when you're done, just once integrate out. And like that. So I've got some sequence, and let me label the macrostates, the sequence I1, I2, I3, dot, 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 In. I want to know what's the probability of that whole sequence. I'm going to get start with my row, I restrict, I evolve sometime delta t. This is the evolution operator, so I can just exponentiate to evolve. So this is I project again, I evolve again, dot, 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 I project to the last one, and spread out. So that's a general formula that's telling me, given some initial probability distribution, what's the probability of a given history, a given sequence of macros. And set out that way, that's a fairly general, if in some ways a little too abstract to do much with, practically formalism for thinking about the kind of dynamical processes we tend to look at in statistical mechanics. What we're interested in those processes is some description of the system at some macroscopic or coarse-grained or averaged-out level, where we're not interested in every detail, but we're interested in some coarse-grained details. What we're interested in when we end up calculating, as a practical matter in modern statistical mechanics, is how initial probability distributions induce probability distributions over the histories of those macrostates. In a lot of situations, then we're playing law of large number games, and we have probabilities over given macrostates that are either really close to 1 or really close to 0. So when we study the Boltzmann equation, even if you study the Boltzmann equation probabilistically, as Boltzmann didn't, but as a lot of modern textbooks do, the probabilities you get out end up being very concentrated on a particular situation. But not everything needs to work that way. If you think about Brownian motion, where the macrostates are labelled by the location of the thing being kicked around, and I'm not interested in the things that are doing the kicking, that's a stochastic process. And the sequence of states I get is going to give a non-zero probability to a whole bunch of different histories. If you think about the role of dice or something, that's another example of the kind of thing where the dynamics of the system is going to be at the macro level stochastic. And a lot of what we're interested in statistical mechanics is calculating this kind of thing, and because this is kind of quite coarse-grained, a lot of the time I can get away with certain approximations for how the dynamics is going here, which doesn't worry about tracking a lot of fine-grained detail, because the fine-grained detail doesn't, or putatively doesn't, make a difference to the integral.
Why do you call that last thing, third thing, history dynamics rather than macrodynamics?
I could have called it macrodynamics. That would be just fine. If I let me do that. Okay, so look, everything here at the moment is exact, although usually not calculable. Give me any old probability distribution you like. Give me any old decomposition of phase space you like into macrostates, and this machinery will generate a probability distribution over macrostates, over macrohistories. So, what it won't do in general is generate anything that deserves the name dynamics. So for something to count as a proper macrodynamics, we want it to be something, to have something like the following properties: to know what the probability is of a given macrostate conditional on a given history, have been to be determined in some relatively simple and relatively time-independent way by the current macro state of the system and maybe a short period of its previous successors. It had better be the case that I can write down something like differential equations or some integral differential variant of them that tells me how the dynamics plays out on the space of macro states in the normal kind of physics way. Notice this is what we have with something like the Boltzmann equation, where knowing the macro state at time t suffices to determine the macro state at time t plus delta t without any need to know what the individual micro details are beyond that.
Brownian motion of a pollen grain and a gas, those stochastic, would also be an example.
Exactly, yeah, precisely. And a lot of systems in statistical mechanics you run into, they might have a certain amount of memory. It might be the case that a certain chunk of their earlier history matters, but at some level I can tell a self-contained dynamical story about the system which doesn't care about the micro details beyond beyond knowing how they determine the macro states. That from the face is kind of striking that it should happen. There's nothing logical to find that should necessarily happen. Why does it happen in statistical mechanics? Well, generally speaking, it happens because the macro states are labelled by some kind of collective or large-scale degrees of freedom, and we can more or less get away with kind of averaging out or not worrying about the small variations in the micro degrees of freedom. There's a lot hidden in the more or less get away with, of course. We know from the various arguments that David's shown that given that the macrodynamics has a tendency to do all sorts of time reversal non-invariant things, given that the macrodynamics tends to give us increases in entropy, given that the stochastic processes tend to run in one way, that it can't be the case that in full generality, for any old choice of initial probability distribution, we'll get a macrodynamics that's in any sense robust or is the same in all cases. But we've also seen that in the situations we're interested here, it seems to be the case, or it seems at any rate to be pretty plausible, that if your initial probability distribution is not too crazy, so maybe it's the uniform distribution, or maybe even if it's highly non-uniform, but not made non-uniform in just the right way to mess us up, if that's the case, then firstly, it does give us some kind of autonomous dynamics, and secondly, it gives us an autonomous dynamics that's not too sensitive to the fine details of that distribution. Let me pause on that actually, because it's kind of weird. And you'll see how this is relevant to the quantum mechanics in a minute. Say I've got some macrodynamical process, like Brownian motion, which is stochastic, and we ask, well, where did the probabilities come from in this deterministic dynamical theory? And the answer, of course, mathematically, is that they came from the initial probability distribution I put in. Probabilities in, probabilities out. The striking thing is that in some sense, though, they're basically independent of the initial distribution, in the sense that I can vary the initial distribution very widely and it basically won't affect the probability dynamics at the macro level. I can put in a whole bunch of possible starting probability distributions into Brownian motion, provided they're not too crazy, and I'll get out basically the same Brownian motion macrodynamics. So in one sense, the macrodynamics is pretty much independent of the details of the initial distribution. In another sense, it's totally dependent on it. Given a set of macro histories, I can define more or less any probability measure over them I like and find an initial probability distribution that will generate just that probability measure. So there's a sense in classical physics, there's a sense in which we get a really solid autonomy of the probability of the macrodynamics, and another sense in which we don't get an autonomy at all. And this gets us deep into the woods of how we're supposed to think about probability distributions in classical mechanics at all, and that gets us, depending on your proclivities, it gets you towards the kind of Humean story that David was telling, or it gets you towards typicality concerns, or it gets you in a number of different directions. In any case, it gets you to a position of thinking, well, the probability distributions used in classical statistical mechanics are doing a lot of work and are pretty mysterious, and we better understand them, insofar as classical mechanics is the right story. Okay, let me say one more thing about this kind of classical story before I close this warm-up with the quantum theory. What makes a given choice of macro states right in classical statistical mechanics. I mean, it's often tempting in the, you find in the literature, often you're told that the reason you should like the reason we use a certain macro distribution is the macro distribution lumped together states of interest to us in some sense. So somehow the macro states define the features of the system that are interested different from our point of view. So it starts looking like a very epistemic notion, a very human notion. I think that's actually hard to defend when we consider how this plays out in the macrodynamics we study. So there are a very large number of macroscopic dynamical systems about which I do not give a damn. I am totally uninterested in the transport equations that apply to, let's say, the 14th kilometre along the Amazon River. I'm still pretty damn sure that even though I don't care about them, they're pretty reliably governed by the kind of macrodynamics that we derive in statistical mechanics for viscous fluid flow. Conversely, there might be things that I'm really, really interested in, but the mere fact I'm interested in them doesn't cause it to be the case that there's some autonomous, well-defined, robust macrodynamics that governs them. I think the real criterion to see what makes certain macrostate divisions relevant is simply the very fact that we can write down an autonomous macrodynamics with respect to them. Yeah. By its fruits shall you know it. You know, if you can find, in some non-contrived and non-kind of cooked up in advance way, some decomposition of the phase space into macro states such that there is an autonomous dynamics defined on those macro states that's robust in the ways we've been discussing, then you found some objective fact about the system. It's a higher level fact, but it's nonetheless an important objective thing that you have discovered. Okay, so much for classical mechanics. Pause for a second, remind myself what I did say. Something profound. Okay, let's think about quantum mechanics. Let me clear myself some space. So let's start by thinking about quantum mechanics at a very abstract level, about the same level as Shelley's first slide. So I have something like, in this kind of framework, the state, quantum dynamics, let's say quantum state dynamics, the state is something like a Hilbert space vector, up to phase if you're feeling pedantic. The dynamics is something like the Schrödinger equation, something exactly like the Schrödinger equation. I mean, just to pause incidentally to flag something that sometimes gets missed in some of these discussions. Specifying quantum mechanics in the sense of just saying I specify a theory by saying I have a Hamiltonian and a quantum state and it evolves unitarian and a Hamiltonian is kind of like saying that a classical theory is described by phase space and a Hamiltonian phase space and the evolution of points on that phase space. That's the description of the abstract framework of classical mechanics. That's the criterion for a given dynamical theory to count as a classical dynamical theory in this framework. But of course, any given classical dynamical theory looks a lot more complicated. The theory has a whole bunch more structure used inter alia to define the Hamiltonian and to set the theory up properly. So any given classical theory is going to be much more structured than simply phase space and the evolution of a point on phase space under a Hamiltonian function. Any given specific quantum theory, likewise, is going to have a whole lot more structure that way. How the structure is introduced in classical physics or quantum physics will vary a lot from case to case. So, in quantum field theory, for instance, the additional structure comes in the form of maps from space-time points to operators. In quantum particle mechanics, the extra structure comes in inter alia in terms of the decomposition of the Hilbert space into subspaces, and in terms of the action of the symmetry group of space-time on those individual Hilbert spaces. All of that I mean mathematically. Is legit, when I say the action of the symmetry group of space-time, I mean the action of the object mathematicians call the Galileo group. So this isn't meant to be an ontological or metaphysical or philosophical claim, it's a mathematical claim about the way a theory is given. Anyway, that's preamble. Notwithstanding all that, quantum state dynamics looks something like this here in the abstract. And if we were just given this theory, we could coherently ask ourselves, okay, what is this thing like? But it doesn't look like this, it doesn't look like history dynamics. History dynamics just isn't given by differential equations in a smooth way. But if all you had is that mathematics, nothing there particularly picks out whether quantum dynamics is about state dynamics, whether it's about telling me how the actual physical state of the world evolves over time, or whether it's more like probability dynamics, telling me how the probabilities of some underlying facts or something or other evolve over time.
You're talking about now, it's a question of not of mathematics and of physics.
Absolutely, yeah. Nothing in the maths will tell you that. Here's a kind of metaphor to take it the other way around. You can imagine just being given this theory as a mathematical theory, and actually you can imagine kidding yourself into thinking it came with a measurement problem. Yeah. Because you could think that you can imagine this theory telling you that the given physical objects were highly delocalized across very different positions of momenta, and that making measurements on these systems spontaneously localized in certain areas. And you can imagine kidding yourself into thinking that there was a profound dynamical problem with this theory. And of course what was really going on would be, it was a probability dynamics, and if you thought about it, you'd realise there was an underlying microdynamics for individual states that generated it. So prima facie, it looks as if the quantum state could be either of these things. Nothing just in writing that down before we start thinking about how it works and how it plugs into experiment would cause us to think one thing rather than another. So the question arises, what is the right way to think about it? Spoiler alert, it's not a probability distribution. But with that spoiler alert out there, let's think a minute as to quite how attractive that prospect in principle can seem. So when we think about how we get empirical information out of quantum mechanics according to the material we learn in the textbook, the way we get empirical information out of quantum mechanics is, as David pointed out yesterday, via the Born rule. This thing, given any operator that's supposed to represent some observable, generates a probability distribution over possible values of the observable. So just remind ourselves, I've got some self-adjoint operator x, and it's got this spectral decomposition. I should say, my training in physics, so infinite dimensional problems and continuous spectrum things have been swept far away under the carpet. So this is the operator here is a nice friendly thing with a discrete spectrum. If this operator is supposed to be, whatever that means, representing some physical quantity, then the Born rule tells us the probability of the quantity giving value xi is going to be given by that formula. And it's through the Born rule that all of our data comes. And insofar as we would be allowed to think of the quantum state as somehow a probabilistic entity, then this would be an unproblematic and natural thing. It's fine that the way we get information out of probabilistic entities is just via what they tell us the probabilities are. That would be okay. Similarly, insofar as the quantum state can be in macroscopic superpositions, that's a profound philosophical problem insofar as it's supposed to represent physical reality. If somehow when I say the quantum state is 1 over root 2 live cat plus dead cat, I'm saying something like the actual physical state of the world is this state, then I've got a real problem in trying to understand what it is. Maybe I can solve that problem a la Everett, maybe not, but in any case it's a big prima facie problem. if all I'm saying when I say it's a superposition of live cat and dead cat is what I would be saying if I said that the probability distribution was half peaked on the live cat region of phase space and half peaked on the dead cat region of phase space, that would be totally unproblematic. Likewise, if after measuring it the system is determinately in the dead cat state rather than in the 1 over root 2 live cat plus dead cat state, if I'm thinking about the state as physical, then I seem to have violated the Schrödinger equation. If I'm thinking of it as a probability distribution, I'm just conditionalized. As I say, I think this way of thinking about the quantum state is ultimately indefensible, but I just want to put some of that stuff out there because I think an honest observer has to acknowledge it's kind of suggestive. There are certainly probability-ish things about the way the quantum state behaves. I mean, one way or another we want to understand why that is if we want to reject the kind of flat-footed answer that's because it is a probability distribution of some kind. Well, why isn't it a probability distribution? Well, there's all sorts of fancy mathematical ways to get at why just regarding it, think things like this directly as telling us probabilities of things isn't going to work. But it goes kind of deeper than this, and in some ways it's simpler than this. The reason why I can't straightforwardly think about the probability distribution just goes back to the old interference experiment situations. So I set up an interferometer set up with a photon or something, photon comes along, there's space here, you're going to have to remember the top left corner. Whole of the left side. I've just got the usual kind of setup. I put a photon through a beam splitter, I do it one photon at a time. I tune the beams so that all the detections end at A. The flat-footed, straightforward probabilistic reading of something like the quantum state being 1 over root 2 this beam plus this beam is, it's either in this beam probability half or in this beam probability half. If it's in this beam, conditional being this beam, the probabilities have to be half A, half B. Conditional being this beam, probabilities have to be half A, half B. So independent of which beam it's in, the probabilities should be half A, half B, but of course they're not. So interference is what makes it impossible to do a completely straightforward probabilistic reading of the quantum state. And attempts to do non-straightforward probabilistic readings of the quantum state have run into more and more and more difficulties, more and more ways of showing that this is impossible or the next best thing. But all of it really comes down to the fact that we have interference phenomena going on. And if you like, all of it comes down very straightforwardly and flat-footedly at the beginning to the observation that if you were allowed to think about alpha catalyzed, alpha spin up plus beta spin dead as being some probability of up and some probability of up plus dead, I'm sorry. If you're allowed to think of alpha up plus beta down as being some probability of up and some probability of down, then what the heck were the phases doing there in the first place? Okay, so here's a claim. One way of thinking about the way physicists use quantum mechanics, perhaps not back in the day, but in practical use now, is something like this. In the microphysical situations, in the setups where we're doing interference experiments, we talk casually, unproblematically about the quantum state as if it was a physical state. When we're dealing with macroscopic phenomena, in particular when at the end of the whole experiment we want to read information of, we change our mind and suddenly we start thinking of it as a probability distribution. And so that kind of, from that kind of perspective, that kind of incoherentness, that shilly-shallying between these different incompatible readings of the quantum state can be thought of as the kind of confusion that's driving the sort of middle of the measurement problem. Here's how that description of the measurement problem looks kind of a little bit different from the way David's saying it. Not in conflict with it, there's a different perspective on it. And the answer is something like this. Suppose you think that that's the way things are going to start, and you also think, well, of course the quantum state has to be a physical thing, and you want to make sense of what you're doing in that physical setup. Then pretty much the only way you're going to be able to do it is you're going to have to say that the probabilities come out by some dynamical transition of the state into one of the eigenstates. It comes out by something like a projection postulate. So you could think about saying, well, your basic minimal starting point is going to have to look like that. And so the unsatisfactoriness of the projection postulate, that's the measurement problem. But I think in some ways it's more helpful to think of that as the first step towards a doomed solution of the measurement problem. And it's notable that in contemporary uses of quantum mechanics and physics, one hardly ever, that outside quantum information context almost never, actually sees someone use the projection postulate as opposed to the Born rule in doing quantum mechanics. I mean, here's a quick anecdotal story. When I originally learned quantum mechanics, I was kind of, because I was taught by quantum information people, I was kind of aware of the measurement problem relatively soon. And one of the things I remember being really puzzled by was the fact that as a collapse of the wave function, it would have to be superluminal, and so somehow it seemed to have to pick out a third basis. And it seemed to me it was then going to be really difficult to see how you'd possibly formulate the collapse rule in a relativistic quantum theory like in quantum field theory. And so I was looking forward to when I learned quantum field theory to seeing how the axioms of quantum mechanics would be laid out in the quantum field theory textbook and what the quantum field theory version of the collapse rule was. And it really confused me to find that, I looked through several books of quantum field theory and there's no mention of this at all. There just is no collapse postulate mentioned in the theory. And the reason for that, I take it, is because what we use quantum field theory to do is to calculate quantum states, always using the unitary dynamics, never using a collapse rule, and then we read off probabilities at the end of the story using the Born rule. So the claim is, in practical physics, the Born rule is being used all the time, but we only really find ourselves using the projection, sorry, the other way around, but the Born rule is used all the time, but we find ourselves using the collapse rule basically hardly ever, and basically only in foundational discussion contexts. Okay, so if that is the measurement problem, then the question it looks like it's going to be, okay, if the quantum state is really going to have to be thought about as physical, how do I recover, among other things, all the stuff that comes out from this kind of probabilistic rereading of it? How do I recover the kind of the kind of objective probabilistic conclusions that are supposed to happen? And how do I get around the problem of macroscopic indefiniteness that comes if I start regarding superpositions non-probabilistically? How do I handle showing that? I'm actually not going to come at the problem directly that way, and this is why I dragged you through all that classical mechanics. Because I want to ask a slightly different problem. If it's so incoherent and confused when I should use one reading of the quantum state and when I should use the other, and if it's just totally unclear how I get between these perspectives, and if I ultimately can't get away with treating the quantum state systematically as probabilistically, how does physics get away with all this? And there's a traditional answer you often see in the philosophy and foundational literature, particularly in the older part of it, which is something like it gets away with it with a massive tower of ad hoc contrivances. And I think if you were looking at even conceptually careful physical literature of the 40s to the 50s, perhaps even a bit later, that was probably fair enough. And this is the period where everyone is genuflecting at the altars in Copenhagen, and this is a situation in which all sorts of talk about the need for a fundamental classical language being used in parallel with the quantum language, all that stuff is in play. And maybe it was the case that the way people handled this kind of thing was to very ad hoc use the language of classical physics to talk about their measurement processes. I don't think that's actually an accurate description of the way physics handles these things now. And in one sense, we can see it couldn't be really, because modern quantum mechanical measurement systems are themselves extremely complicated, advanced physical systems whose operating principles normally involve quite a lot of quantum mechanics. So anything as simple as just saying, we'll resort to classical mechanics to describe measurement, or we'll just treat measurement devices as primitive black boxes, isn't a plausible way contemporary physics could be, given it gets on fine doing these really quite complicated, carefully set up activities. And I think physics has a story to tell about how we make sense of and get away with these moves. That story isn't a solution to the measurement problem, but that story goes a lot further and gives a lot more structure than I think is entirely recognised in some of the foundational discussions. So I want to lay some of that out. And my starting point is going to be something like this. What we're looking for, formally, structurally, never mind the philosophy, never mind the ontology for the minute, is some route within quantum mechanics by which I can construct, can derive macro-level equations for large-scale mesoscopic, macroscopic systems of the same kind that we found ourselves deriving in classical mechanics. And incidentally, we better have access to, it may be the case that there is some kind of discipline and some structure of that kind in contemporary physics, even apart from the analysis of measurement, because a whole lot of the discussion in modern physics of how we get macroscopic dynamics out of microscopic systems is done in quantum theory. I mean, as a silly comment on this, just to remind ourselves how strong this is, sometimes you have discussions that go things like, well, of course, if classical mechanics was true, then blah. If classical mechanics was true, then I'd say this. But because quantum mechanics is true, I'll say that. And of course, in a certain sense, that's perfectly fair counterfactual, but to remind yourself, classical mechanics is true, I wouldn't say anything, because matter isn't stable. I wouldn't stand it. So it may be the case that somehow there are within physics techniques and pieces of machinery that let us do these kind of games in the quantum space as well as in the classical space. We can ask ourselves, qua philosophers, qua philosophically sensitive physicists, how, if at all, can we understand that machinery? What's wrong with it? What maybe needs to be added to it or modified in it to make it coherent, make it make conceptual philosophical sense? But a good starting point is to see what it is. Okay, so here's a way of thinking about that. What are the circumstances, if the probabilities in my theory are generated by things like that, what are the circumstances in which probabilities generated in this way will indeed obey the probability calculus more or less? In this case, they don't obey the probability calculus. If I use the Born rule to work out the probability of the photon being here and the probability of the photon being here, then I won't find the probability calculus is satisfied when I use the same Born rule to work out the probability of being here. But there may be some circumstances, given we get away with this move, there may be plenty of circumstances, and they better encompass most of the macro realm, in which we can get away with that. Let's think about how that can run. Let's suppose we've got some observable, which is supposed to be representing some macroscopic quantity that we're measuring. Let it continue being this ubiquitous X thing. And let's think about what the probability would be, according to the rules of quantum mechanics, of obtaining a sequence of measurement results of this operator X, representing, supposedly, in some philosophically dubious way, some physical quantity. And there's various ways of setting this up, but one of the most flat-footed and straightforward ways is just to think in terms of the projection postulate. So, how does the formalism give me a probability for this measurement result, plus this measurement result, then this measurement result, then this measurement result, and then this measurement result? Does it something like this? Start with the state here, project onto the eigen subspace corresponding to this result. Evolve forward under the Schrödinger equation. Project again. Evolve forward again, project again, keep doing it. At the end of that process, take the mod squared amplitude. So mathematically, here's what that looks like. Let me put the operator up again to remind ourselves. Start with the state. Apply the projection postulate for the first measurement result. Evolve. Project. Evolve. Iterate, do the last evolution, the last projection, mod it squared. So quantum macrodynamics has that form. And that's not meant to be a foundationally loaded claim. I'm not making any claim about the sensibleness or philosophical coherence or making sense of this. The claim is just that's how the machinery of quantum mechanics gives us probability distributions over sequences of states at the meso or macro level. Okay. Who's come across this kind of formalism before, by the way? People. This is the consistent history of formalism, just to put a name to a face, so to speak. Here's a thing about, I mean, look at this expression and compare it with this expression.
But that formula itself is just a Wigner formula.
Oh yeah, there's nothing,
it doesn't become the consistent history formula until you say formalism until you say more.
Agreed. Yeah. Sorry. This is the beginning. This is the beginning of the chunk of the formalism. Yeah, you're quite right. And I should say I'm not actually going to give you all of the kind of quantitative details of the formalism because I think I'm already riding towards the top of how much maths I can get away with on a sunny Friday afternoon. Oh, that's the optimistic take, anyway. Okay, so this formula has got a lot in common with this formula on the surface, yeah. But the kind of projective old, iterate at the end of the day, get a probability out, has the same kind of formal idea there. But because this thing is squared, then there's an important mathematical difference between these two stages. In this case, it's automatic, I mean by construction, it's automatic that these things satisfy the probability calculus. In the sense that if I were to consider using the same formalism to generate the probability of a more coarse-grained history, in which, for instance, I don't give a damn about what the system is doing at time t3 plus something boring, then this formalism is just guaranteed to give me numbers that add up in the right way. Of course it is, I just built it that way. I started with something that's explicitly probabilistic. I worked out what the probabilities were for each history. If they didn't obey the probability calculus, it's just as my maths got. It would just have to look at my math answer. These things don't, in general, obey the probability calculus. You can see why they're not going to obey the probability calculus, because something which is going to be quadratic in the various terms in the history, if I were to work out the probability of some coarse-grained history, it's going to have a whole bunch of cross terms, and in general the cross terms are going to mess with the probability calculus. And the cross terms are just the way this formalism is representing interference. So I won't go through the whole story, but if you imagine running this formalism on a nice simple starting point like this and just say, well, my histories just have two steps. I'll ask, is the system here or here at time 1? And then I'll ask, is the system here or here at time 2? There's going to be fine-grained histories like here and then here, or here and then here, but there's also going to be coarse-grained histories like never mind when it was here, all I care about is it ended up here, and never mind when it was here, all I care about is it ended up there. And if you use this formula to work out the probabilities, while you will give the right formula for what the probabilities would be, if you in fact made those measurements, you won't generate a set of probabilities which self-consistently define a set of probabilities that obey the normal probability calculus. And a way of thinking about that, if you like, is that the measurement is unavoidably messing around the system. This is the old thing you learn right back in your undergraduate level quantum mechanics. If you look which way the particle went through, you mess with the interference. Alright, so generally speaking, calculating probabilities in this sense doesn't calculate probabilities here. Tim warned us a couple of times that just because something has the formal structure of probability distribution, that doesn't make it a probability distribution. Having the formal structure of probability distribution is not a sufficient condition to be a probability distribution, but at the very least be a necessary condition. However, in a number of important cases which look suspiciously similar to the classical cases where my projections are onto something like centre of mass positions or systems or collective degrees of freedom in some average sense of large systems or something like that. In cases like that, we tend to find two things happening. Firstly, the histories turn out to be consistent, or near enough, consistent to within one party to 80 or something like that. And Furthermore, they tend to turn out to be consistent in a way which is robust against changes of the quantum state. And secondly, under those same kind of conditions, we get our probabilities of the histories which not only obey the probability calculus, but define a probabilistic dynamics in the way I was describing for the classical case. In other words, which define a set of probabilities which can be analysed as something like the playing out of a set of stochastic or deterministic differential equations. So notice the similarities, but also the differences with the classical case. In the classical case, any old macrostate decomposition and any old choice of initial quantum state generates a probability measure, but the striking feature of the of the particular macro process we look at is that the probability measure is pretty robust, though not totally robust, against modifications of the initial distribution, and it can be described in a relatively simple way using some kind of stochastic differential equations. Difference equations, actually, in this setup, in any case. In the quantum situation, formulae of this kind in general won't determine a probability distribution at all, at least not one that satisfies the calculus. But for the kind of systems we're interested in, there's certain kind of systems that StatMech tends to study and that looking at macroscopic goings-on tend to look at, then we tend to find, one, we get robust probabilities, things that behave like probabilities at all, and two, not only do they behave as probabilities, but they're kind enough to behave as probabilities in a way which gives us dynamical equations for those macro conditions. Notice another kind of similarity, kind of difference between the quantum case and the classical case. In the classical case, while the macrodynamics being defined was pretty robust against changes of the initial probability distribution, it wasn't totally robust, and there were probability distributions that could give me a completely crazy macrodynamics, or more or less any macrodynamics I wanted. In the quantum case, the kind of systems we're interested in, it's not generally the case that I could choose an initial quantum state that gave me some set of probabilities that weren't the kind of robust probabilities I wanted. The circumstances in which I get out robust, well-defined probabilities are pretty much the same circumstances in which I get out things that behave like probabilities at all. And let's just pause a minute to see why that is, or to think heuristically about why that is. In the classical case, the reason why I was able to do something like write down fairly autonomous dynamical equations for the macroscopic degrees of freedom was something like, there were so many microscopic degrees of freedom, they were all doing their own thing, and one could use statistical methods to more or less average out the whole thing, so you didn't need to care too much about the fine details. In the quantum case, where that phenomenon is going on, it's also the case that I've got a whole bunch of small degrees of freedom into which the quantum coherence can diffuse. This is the other route to decoherence, the more dynamical route that David talked about yesterday, where systems are being constantly observed by their environment and getting entangled by their environment in such a way that interference phenomena within the system become enormously suppressed. And many, from a certain perspective, pretty much all the systems we're thinking about here have that character. Although it's important to remind ourselves that environment here doesn't need to mean some spatially distant system. It can perfectly well mean the high energy modes of some system decohering the low energy modes. It can perfectly well mean the kind of spatial averages over medium regions of a gas, quantum mechanically represented, being decohered by the fine-grained details of that gas. So the same machinery, which gives us quote probabilities which behave like probabilities at all, also gives us probabilities that can be governed by some kind of autonomous stochastic level equation. Okay, a couple of thoughts about that, and a lot of what I'm saying here, while I'm thinking about it, it's all in the context of unitary quantum mechanics, but beyond that it's interpretation neutral, so even if it's clear to you that the Everett interpretation is insane and should be touched with a barge pole, quite a lot of this still goes through to generally how we handle quantum statistical mechanics. So think for a second about how time reversal asymmetry, the asymmetry of time in statistical mechanics plays out in this quantum case. I've got out some kind of, generically speaking, stochastic macrodynamics, at least in the formal mathematical sense, using this kind of technology. It's in the nature of dynamics of that kind to have a kind of branching structure. So they have an asymmetry in time, they have a directness in time. Where did that come in? Well, just as in the classical case, it has to have come in the boundary conditions. I mean, this is more or less analytic. If the microdynamics is time symmetric and the macrodynamics is not time symmetric, the only place you've got available to break the symmetry is the actual contingent state you're doing the dynamics on. So something in the initial state is breaking the time reversal, is messing with the time reversal symmetry of the theory, in the classical case as in the quantum case. But notice, in the classical case, this probability distribution has to be thought about as a probability distribution. And I can perfectly well think that the right way to say what's really going on when I say this probability distribution is chosen so as to give me time reversal, time asymmetric stat-mech type dynamics, is to say that pretty much all of the individual states where my way of determining pretty much is given by the probability distribution are individually the kind of states that display thermodynamic, stat-mech, diffusion type behavior. In quantum mechanics, I can't do that because this is just the physical quantum state. We've already said we're not going to interpret it fundamentally probabilistically. So the claim that's delivered by the uniform probability measure that David was talking about in David's approach to stat-mech on Monday and Tuesday, which requires me to add some explicit probabilities to the theory in order to understand it, to get out the asymmetry in an appropriate way, is being delivered here. It requires some condition on the probabilities. Here it's being delivered by a condition on the actual state. So in philosophy jargon, the constraint on initial conditions required for classical statistical mechanics is at least prima facie dispositional. In the quantum mechanical case, it's straightforwardly categorical. Quite how you cash it out in a clean way, you could have as open to question, but it's going to be the case, and unproblematically, there will be the bulk of the quantum states in some relevant sense will deliver you the right kind of stochastic dynamics. Chris.
In the quantum context, I thought that GRW was such that the dynamics underlying dynamics is simply asymmetric, in which case you wouldn't break the symmetry.
Right, when I say the quantum context, I'm sorry, I mean the unmodified unitary quantum context.
Oh.
You're right, GRW changed the rule. Yeah.
Can you just give me a gloss on what you mean by dispositional there? I mean, if I were to say, in David's picture, the asymmetry is really coming from the past hypothesis. And that's just categorical, right? That's just saying a macro state was. And that then that together with the typicality analysis on Shelley, I mean, I would the typicality analysis kind of dispositional. You just said that's dispositional, not, there's a sense of disposition.
Yeah, that's why I edged and said prima facie. So if one didn't like the dispositionality aspect of that, you could, for instance, handle it by a typicality move.
Okay.
But of course, I mean, as you know, just to remind people, the past hypothesis, the low entropy hypothesis by itself doesn't deliver the right thermodynamic behavior. There are plenty of states which start with low entropy and evolve into an even lower entropy. Okay, so another observation is coming out of this, and again, this is a fairly interpretation-neutral comment, at least up to a point. In the classical case, I kind of banged on about the fact that all the probabilities come out of the statistical distribution I put in the beginning. In the quantum case, the probabilities that we get out in quantum stat-mech are basically quantum probabilities to start with. I can take a pure state, this is a pure state, there's no hypothesized ignorance about which state it is, and I can evolve that forward, and that state by itself will evolve into a superposition of these various history terms, and they'll all get their different probabilities. And the probability will be fairly independent of what the state is. So there's an important sense in which, even before we start considering the GRW strategies that Chris mentioned, that David's talked about, the quantum and the statistical probabilities are going to be very, very merged together. here's another observation about time asymmetry in this story. Suppose we think about, let's say, the present epoch, or the system of our ice cube that's part melted, the example we're talking about. If we in the classical situation, if I take that state and I time reverse that state and evolve it backwards, what happens is that the state will make its way back down to reliably to the initial starting position. And that's true even if I had a stochastic process. If I had classical Brownian motion, let's say, and the actual system has made its way jiggling around and has finally come to rest over here, if I were to time reverse that system and then go back, it will reliably make its way jiggling back to here.
But David,
Yeah.
I just want to make sure I understand. That doesn't sound like it's true unless you also time reverse the stuff.
Oh yeah, absolutely. Sorry, I don't just mean
Not
time
a
reverse
genuinely stochastic
Yeah, I don't just mean
process.
time reverse the pollen grain. Time reverse the whole shebang.
Yeah.
Right, that's really the deterministic situation.
Right.
Exactly.
Certainly
yeah.
wouldn't be
That's
true.
right. It's the stochastic. I mean, even what you mean to time reverse a stochastic differential equation is problematic. But we're time reverse the whole deterministic system. If we time reverse it, we don't get out the stochastic dynamics as applicable to the system. We get out a particular time reverse routine. That's basically not true in a lot of cases in the quantum theory. Here's a nice kind of thought experiment to think about. Suppose I've got a neutron. I have a neutron delivered to me by Amazon from some, presumably before long Amazon will be delivering things fast enough that the decay times can be neglected during the delivery process. So a neutron's sitting on my desk. I leave it for 10 minutes or so, and as it happens, it's not decayed. So if I take that neutron and I consider the quantum dynamics of that system over the course of the next 10 minutes, then I'll get a quite complicated superposition. It'll be a superposition of a term with the neutron undecayed and a whole bunch of different terms with the neutron decayed at different times. And on the basis of that, I can think about the various times at which the neutron decays as being characterized in something like this history framework. I can apply it, although the neutron doesn't seem like a macroscopic system, from this point of view it is. You can think about the neutron degrees of freedom as being decohered by I don't know how you set it up, but in something like the very many different ways I can set up the electrons and neutrinos and protons and things produced by the decay process. In any case, the mathematical structure of that fits into this kind of story, and I get out perfectly happily the decay process of the neutron. Say I take the neutron and I evolve it back. I take the actual state of the neutron, an undecayed neutron, and I evolve it backwards in time instead under the Schrödinger equation. The prediction of the Schrödinger equation is not that the neutron remains undecayed, which is what was actually true in the past. The prediction of the Schrödinger equation is that the neutron evolves in a time-reverse way into a superposition of an undecayed neutron and a whole bunch of time-reverse decayed neutrons, which isn't what we saw. What's going on mathematically? How do we reconcile that with the fact that no one screams that the Schrödinger equation is being violated by neutron decay? It's meant more as a technical than a philosophical question, although it's philosophy below the surface.
You're losing all the, you have to, if you really actually wanted to get the time reverse thing, you probably have to start
Right.
with a very strange state at that later time.
Yeah.
One you would never start with.
Exactly. Yeah. So think about the neutron as soon as it arrived from Amazon. So the neutron, over the 10 minutes before I ran the experiment, the neutron already evolved into another of those superpositions of undecayed neutron plus a whole bunch of different decayed neutrons at different times. If I want to do a time reversal, it's not okay to just time reverse my actual neutron. I've got to time reverse the whole quantum state, including all the various quantum states corresponding to what I didn't actually observe happening. I had to evolve all of that, and now, while it's true that my neutron, the actual neutron undecayed state evolves into a superposition of decayed and undecayed states, the other decayed states also evolve into superpositions of decayed and undecayed. And because precisely of how the system is produced, the phases of the various undecayed states are lined up in just the right way that all the decay states negatively reinforce and cancel out, and all the undecayed states constructively reinforce. So the result of evolving the whole thing backwards is that I get back to my required neutron. Yeah.
So it's that to say that in order to preserve the time reversal symmetry, you have to consider the state as in superposition the entire time, no matter what direction you're evolving in it?
Well, it's an interesting point, isn't it? To evolve it forward, I don't need to consider the whole state. Why don't I need to consider the whole state? That's really another way of talking about the decoherence condition. If I've got this kind of condition holding, that these things work as probabilities, that's just enforcing the fact that there isn't actually going to be any interference between any given term and other such terms. But to do things into the past, yeah, I've got to keep the whole lot. So this is kind of quite a striking thing about unitary quantum mechanics. If you don't want to violate the Schrödinger equation, you have to keep in play, for backwards time evolution, you need to keep in play not just the quantum state that's supposed in some way to be corresponding to what your actual surroundings are, but all the rest of the quantum state. And that's interpretation neutral. That's true for the Bohm theory as well. It just follows from the unitarity of the Schrödinger equation.
So it seems like you have decoherence for the future and recoherence towards the past.
Yeah, exactly.
So where does the fundamental time asymmetry come from? What part of the boundary conditions does it come from?
Okay, so this is mathematically the same classically and quantumly, but it's kind of made a bit more vivid, this point of view. In the classical case, if I take a probability distribution that's not kind of too kooky and carefully concocted, and in the quantum case, if I take a quantum state that's not too kooky and carefully concocted, if I evolve it forward from that starting point, I get forward entropy increase, forward decoherence, forward stochasticness, blah, blah, blah. If I evolve it backward from that point as well, I get backward stochasticness, backward decoherence, backward blah, blah, blah. So in a sense, what I really do is I break the time translation asymmetry mathematically by making that assumption. So you can think about the actual dynamics as having, very kind of schematically, like if I had an artistic talent, I could do this properly, it has a map kind of shape. And you can think about the past hypothesis approach to handling this as just saying, like, do it here, please. Okay, so I labour a lot of that, and a lot of that I've laboured in ways that aren't crucial to the Everett interpretation, just to try to make some connections between how the quantum mechanics plays out in parallel, but not always in parallel, to how the classical mechanics go play out. I think a lot of the foundational work in statistical mechanics is in a classical context. In a lot of cases, it makes sense it's in a classical context. You want to build on work that's been done, but a lot of quite interesting things happen in the quantum case. It's quite underexplored territory, and of course, for a lot of the systems we're thinking about in cosmology, particularly in the inflation type scenario, the quantum mechanics really matters. And incidentally, here's one other observation that comes out of this kind of situation. If for quantum mechanical macroscopic processes, I inherit my probability distribution over macro histories from the quantum probabilities, and I inherit them in a way which is fairly independent of the quantum state, then there's significantly less room for manoeuvre in quantum dynamics than in classical dynamics to suppose that there are other autonomous, robust, high-level theories that aren't in any sense derivable from the underlying physics in principle. So, I mean, David was talking about his approach as being rabidly imperialistic, but there's a sense in which the imperialism is kind of compulsory in a theory that just says, given the actual quantum state of the early universe, I don't need additional statistical claims about probabilities put in to get out the probability distributions that physics will generate over histories. Yeah, David.
David, but I want to get a little clearer about this.
Yeah.
I take it the claim isn't, or maybe I'm wrong. So take some initial macro description.
Yeah.
It might sound to a casual listener as if you're making the following claim. There is no exact quantum state compatible with such a macro description that doesn't, in this probabilistic sense, behave in a thermodynamically normal way. Is that the claim you're making?
No, the claim I'm making, well, first the claim I'm making, as always, is hedged with the it is heuristically plausible that clauses. But,
Yeah. But let it be
the claim is that the ones that don't produce that don't produce what you could call thermodynamically abnormal decoherent behaviour. They just don't produce any behaviour that's describable in a stable probabilistic way at all. They produce a kind of quantum slime or something.
Right. Good. But they produce some kind of a there needs to be a way of neglecting them.
Yeah. No, that's absolutely right. Yeah.
So it seems like this is still going to have in common with the classical case the need for some further way of restricting the microstate, either by means of a probability distribution or by means of some other criteria like separability or something like that.
Absolutely.
Over and above the restriction imposed by the macrostate.
Absolutely.
Okay.
I mean, look at this. Here's a useful way to think. In classical statistical mechanics, the use of a probability distribution over initial states is kind of doing two things. Firstly, it's the source for the probability distributions that occur at the macrodynamical level. The only place to get probability out of a theory of this form is to put it in the first place. So that's one role the distribution is doing. Another role the probability distribution, the statistics of probability is doing, is that we've got heuristic grounds to think that only really kooky and odd states fail to behave in the statistically mechanical normal way,
right.
But we don't. But the term not kooky and really odd, rather like the term measurement or observable, is not supposed to be in our fundamental physics,
right.
And so we use a probability distribution as a way of getting at it differently.
Right.
In the quantum case, those notions come apart.
Right.
The probability distribution that we get out of stochastic macrodynamical processes is given by the quantum mechanical probabilities. But I still need some clause or some method, one still needs some clause or method to rule out the kooky states.
Right.
And one thing you could do, for instance, is say, well, if I were to choose the initial state at random from the Hilbert space ball, let's say, it's extremely likely that I'll get.
Good.
I mean, depending on how you think about philosophy of probability is going to affect how happy or unhappy you are about that move. If you've got some relatively deflation way of thinking about it, like typicality, for instance, then you might be quite relaxed about that.
Right.
If you don't know how to understand that except by introducing some probabilities, you might feel really uncomfortable about having to introduce a new sort of probability that isn't quantum probability, but whose only role is to ensure that the initial state is appropriately non-kooky.
Is there not the possibility, I really don't know, but the structure of states and dynamics in quantum mechanics might afford something that you couldn't have classically, namely the ability to characterize those kinds of wave functions which are going to behave nicely.
Yeah, I think that's an interesting optimistic possibility that I'd be very tempted by. I mean, here's a toy idea, for instance. What you tend to find, what's the only constructive way we know to get kooky states? Answer: evolve non-kooky states forward and time reverse them and look at them. And the kind of states we tend to find there have a lot of very careful long-range entanglements set up in just the right way. So just put so you can heuristically plausibly imagine that some categorical initial state constraint like long-range entanglement falls off exponentially or distance or something might have the ability to do what you're after. That would be a very attractive prospect. Filling in the details of that would depend on your cosmology and is a highly salient topic for this conference, I guess, but it's beyond my pay grade as regards quantum cosmology. Okay, I'm in data design and transcription. I haven't actually talked about the Everett interpretation yet. Where have we got to from the point of the measurement problem? I've been saying, never mind the fact that this thing isn't really a probability distribution, let's characterize the circumstances in which we can get away with treating it as a probability distribution. What's the mathematical fact that we discovered about unitary quantum mechanics as a consequence of that analysis? So here's the claim. I mean, there are places where even the claim is contentious, but I'll try to keep the contentiousness to how one handles the claim. The claim is going to be something like, we've discovered that in a really quite detailed and robust and concrete way, the structure of the dynamical evolution of the quantum state has the same structure as a kind of interlocking set of stochastic dynamical processes. So from that point of view, you can then say, okay, well, if it has the same structure, what, if anything more, do we need to say? And the Everett interpretation line, in its crudest possible term, just says, well, that'll do. If we found that the world has the same structure in a detailed and follow through and concrete and dynamical way at a certain macro level as given kind of macro classical theories, then physics and science in general is only in the business of finding structural contributions of that kind, and we'd be done. We would be acknowledging up front, of course, that the whole quantum state is really physical. We'd be accepting the physical reality of this entire unitarily evolving quantum state, but we'd be saying the way this quantum state has become structured is by an enormously branching process, and furthermore an enormously branching process where the relative mod-squared amplitudes of the branches have the same structure as the probabilities you find in appropriate stochastical dynamical processes. Okay, so if you ask what's problematic about that, you can kind of see two ways of identifying difficulty. One difficulty to identify could be a general worry that says, and this links to some of the things Shelley was saying, that just having enough, just because something is structured in the way of something else, that's not enough to regard it as being as something else. So we could say just generally, just because, let's say, a given branch of this highly branched system has the same structure as a bunch of classical stuff dancing around, that's not enough to make it a bunch of classical stuff dancing around. And a different way of saying what I take is ultimately the same point is to say that we just don't have, although we understand mathematically what's going on there, even to use language like structure in a physical sense, one can worry is already buying in claims that we don't know how to get our teeth into. Another way of putting it is that, I mean, so one thing that you might respond if you didn't like the idea that just getting the structure is enough, is you might say, well, what I need in addition to the structure is, let's say, my local variables or my primitive ontology or something like that. So one way of cashing out the worry that critics of Everett have had to Everett, but also to GRW without something else in it, is that sure, it might be right structurally, but it hasn't got local variables, they need to be put in explicitly. And the other worry one might have is that even if one accepts in general that the right way to understand interlevel relations in science is structural continuity, even if one's prepared to accept that what it is for a theory to genuinely be a theory about tables of chairs is for it to be a theory of the same structure as a theory about tables of chairs, you might think probability is a special case. You might think that this theory is deterministic, the probabilities are present in the theory only in a formal sense. This is exactly the thing Tim was warning us against. We might have something like a formal structured probability, but to be a probability in some essential sense is it requires, for instance, that somehow I have appropriate connections between probability and some frequencies in the world, or some alternative possibilities, or it's conceptually impossible to think about probability where only one thing is realised, or a range of concerns of that kind. And perhaps just to kind of show how one thinks about those kind of worries, notice that now we've got all this kind of decoherence machinery work through, we can think about how other realist solutions to the measurement problem handle that situation. So for the general ontology question, then I'll just defer to many of the things that Shelley was saying this morning. The probability case is perhaps more interesting from this perspective. So if we don't think that we're just allowed to interpret the mod-squared amplitude terms in the branching structure as being probabilities because they're structured that way, then, and we ask how can we put them in? Well, from this perspective, then there are kind of two ways we can put them in. We can add some additional ontology to the theory, which somehow succeeds in singling out only one of the terms in the vast branching superpositions being the term that is physically salient to the world we're interested in. And we can set up that ontology so it has some real probabilities in it, and we can make sure we've tuned the theory so that those real probabilities conform to the mod-squared amplitude of the branch. or we can introduce some kind of dynamical collapse principle which prunes away all but one of the branches, and which prunes it away in just such a way that the probability of a branch not being the pruned branch is equal to the logical analogy of that branch. But very schematically, those are your moves available if you wanted to add a probability to the theory, Tim.
I mean, this is going back just for a second.
Yeah, sure.
It's way too big a possible. The word structure became obviously very important in the last few months. And there's a sense in which one says theory A has the same structure as theory B if there's a nice mathematical isomorphism. There's another sense of, well, many senses of other senses of structure that might be floating around that would clearly not be preserved or guaranteed simply by the existence of such a mapping. So, to take an obvious example that would be relevant to the kind of marvelous point thing, if I have a lot of particles in a low-dimensional space, I can say at a certain moment, just freeze time, look at that moment. There are certain structured objects, right? Tables, and then you can count the legs, and you can say how far apart the legs are.
Yeah.
And then there's a perfectly good mathematical mapping from that to a single point in a high-dimensional space. But if I just freeze that at a moment,
Yeah.
right? Don't worry about the dynamics. Don't worry about anything else. There's just this point.
Yeah.
It's very hard, even though there's this mathematical isomorphism.
Yeah.
Sort of wouldn't say, gee, the four-legged structure of the, you know, I mean, there's going to be some very fancy other kind of analysis if you're going to argue that the single point being where it is in this other thing counts or has the same structure, even has the same structure as a table with four legs that are so and so far apart. So, is there a clear, I mean, do you have a particular thing in mind when you use the word structure and two theories having the same structure, or what guarantees they have the same structure? Is this a very case-by-case kind of thing? We'll just have to look at individual cases and make
I've got a couple of things to say that I'll say in a minute, but let me say something quick in response. So here's a minimal response, which is firstly to be relatively relaxed about your kind of case-by-case issue, but also just to flag that I think the kind of structural isomorphism that I think is going on here is multi-temporal. It would be a case of saying that I have an isomorphism between the dynamical process here and the process here. So in your case, with the marvelous point setup, the fact that the marvelous point at time t could be understood as instantiating the structure of the chairs and the tables at time t is parasitic on the fact, or derivative on the fact that the entire, you know, not the entire overall history, but that a respectable chunk of the evolution of that system also has that kind of dynamical mirroring. And I take it that's going to be general in structural analyses of intertheoretic relations in science in general. So something like, what makes it the case, let's say, that my particular neurological configuration instantiates my believing that snow is white, is not necessarily going to be something that just sort of follows straightforwardly from the instantaneous arrangement of my brain, except parasitically on what I know about how my brain behaves dynamically.
Okay, so anyway, recognizing the relevant structural isomorphism is much more complicated than just noticing maybe mathematical,
I think that's probably right, but let me come back to it, David.
But, well, so maybe you don't want to come back to this, but just to follow up on this point for 1 second. So you told Tim something of what was going to be involved in identifying the point up there in the high-dimensional space as a chair. There's another worry that's raised. Tim just raised it, Shelley raised it earlier on today, that even if there is a way of identifying it as such, it's going to be horrifically complicated. Shelley raised the possibility that it would have a complication level that exceeds the grasp of human intelligence, or something like that. Do you want to comment on that?
Yeah, I mean, I suppose the kind of minimalistic observation is just that the kind of structures I'm talking about aren't exceeding the, well, insofar as there isn't some cheating.
I mean, aren't they the ones that we've just always used in quantum mechanics, in reading off the...
Well, that's the thought, yeah. I mean, so they're not going to exceed the grasp of human intelligence because we've kind of grasped them.
Yeah, I mean, we've been doing it for a long time.
I mean, of course, the worry is that we've cheated. So the worry is that somehow the way we've done that is it has done some kind of smuggling in of something that wasn't really being got in the legitimate way. To some extent, you need to look at the details. So there's a nice observation from Tim, which I think is fair enough, which is that in thinking about configuration space, if you're not careful, you smuggle in the fact that the points in configuration space are the configurations of particles just because you use that name.
Right, or the other way to put it, reading it off a coordinatized high-dimensional space,
Yeah,
where you take for granted the significance of the coordinates is, of course, quite trivial.
yeah.
You say, well, this coordinate just means the position of that particle, and this one means the position of that particle. Of course, that's easy to do, but that's not consistent with
No.
the basic
But
picture of
the
what's
question
going
is
on.
how much more it involves. But,
Yeah.
okay, well,
Yeah, but let's pause on that for a second. I'll come and say some more. I will come and say some more stuff on structure later. But I'll talk about this point example for a minute. So, our example is something like if the real world was genuinely fundamentally a configuration space point moving around, could that be regarded as instantiating the structure of the world in an appropriate way? And I should say that I don't actually think about quantum mechanics in terms of undulating things like configuration space is the right way to think about theory. So I don't want to push that too far. But it's a good thought experiment to play with the idea of structural isomorphism. And I think that here are three different steps one can think about. So at one extreme, if you think I have a point undulating around in a high-dimensional, Euclidean but otherwise unstructured space, then of course that's going to be an enormously difficult recovery project. And at the other extreme, I've got a point wandering around in an already fully coordinatized 3-dimensional space where I've already got labels saying that this point is the position of particle 44. Then of course it's trivial but uninteresting. But I think the right way to think about this as a starting point, I think, is it's going to be a bit intermediate. The space, configuration space regarded as an abstract mathematical space, it doesn't come with explicit coordinates and pointers that say this is particle 43. But of course it's vastly more structured than just ordinary 3-dimensional Euclidean space. You know, it's got an enormous amount of actually writing in differential geometry language would be pretty ugly, but it has an enormous amount of that kind of stuff written into it. And I think some of the kind of accepted, I think some of the literature on the marble point situations has a too attenuated notion of the high-dimensional space in play.
Of course, all that extra structure is both an advantage and a disadvantage. It raises the objection of why is that extra structure natural, which is probably very natural from a low-dimensional point of view.
Yeah, I think it's really unnatural, but that links to why I don't think this is a good way of thinking about the ontology of quantum mechanics.
But let me also just make one other comment. If I accept everything you said, take the case where it is just Euclidean, there's no more structure.
Yeah.
But this guy's wiggling around, as it were, in a way that there exists coordinates. Right? There exists, because the question is, how much do I get out of the observation that there exists a mathematical function, a purely mathematical function, from this to that? It preserves a kind of structure. Right? So it's purely Euclidean, but it's wiggling around in such a way that, in fact, there is a coordinate system, right? That's a mathematical fact. There is mathematically a translation scheme. That, you say, would not per se be sufficient to say the relevant physical structure is shared between two
Yeah.
points.
But I mean, notice that, you're talking about just how the one actual point is wiggling around on the map. What are you, assuming?
Not me.
I mean, there's a lot more. There's a lot more. If one helps oneself to the dispositional facts about what lots and lots of other things would do wiggling around under the same dynamics, you've got a lot more to work with. And I have no very strong view on Humeanism or otherwise, but my confidence on Humeanism or its negation is a great deal weaker than my confidence about the idea that structural isomorphism is the way to think about intertheoretic relations. I'm entirely happy to embrace whatever position of law is most convenient. Okay, so just to go back to finish off some of the thoughts about probability. So I was
But
saying,
David, let me just make a comment, totally not related, I think.
Yeah, okay, go.
When you described how GRW and Bohm can be regarded, I mean, the way you described Bohm was, of course, not the way a Bohmian would think about what they were doing.
Yeah, absolutely. No, I think a Bohmian clearly is not going to think that the purpose of the particle is to simply pick out a certain branch. And a part of the reason for that, of course, is that part of what the particles are doing is giving my actual ontology. So the point's a bit more limited. It's that insofar as understanding probability is concerned, the task is simply to pick out one branch. Okay, so I mean, pause here to see what is prima facie attractive about the Everett interpretation. And I think pretty much everyone coming from really starting point here agrees that it is prima facie attractive. It's just a matter of how much whether that prima facie promise is just deceptive. But it's the only, from the point of view of understanding the mathematics and the structure and the dynamics of the theory, the only thing we gained by lopping off the branches, the only thing we gained by adding the articles was philosophical. We already had all the structural stuff about the probability distributions and all of that present anyway. We did something. We changed our equations. We changed our equations in there, or added to our equations in ways that could get really quite complicated and extensive. More so the deeper into the weeds of quantum field theory you go for this purely philosophical goal. Now, of course, if the goal can only be attained that way, fair enough. But if the goal can be obtained by without them to do that, then that's highly attractive. I mean, in some of this is perhaps a useful thing from a sort of student point of view. From the point of view of kind of popular or semi-popular discussions of interpretations of quantum mechanics, often get the impression that there's a whole bunch of people out there who agree that quantum mechanics should be understood as a description of reality, who concede the coherence of the Everett interpretation as a way of describing it, but who reject it because they find it ontologically profitable or something like that. I think in philosophy of physics, at least, I know very few people in that category. I think the prima facie attraction of a theory which leaves the mathematics unchanged, which leaves the symmetry structure unchanged, is fairly widely accepted. The reasons that the people are not supporters of the Everett interpretation in philosophy of physics is not because they think it's unattractive, it's because they think it's incoherent. Just to clarify some of the what the relevant states play. Is that fair?
That's fair.
Okay. Yeah. Okay. So,
it's unattractive and
so let me go in reverse order and say something about probability from an Everettian perspective and structure from an Everettian perspective. I'm actually going to say rather little about probability. I mean, and my reason for this is kind of a bit indirect. This is a very, very large question. There have been a very large number of different strategies to think about probability in the Everett interpretation. The moves and counter-moves have got quite elaborate and quite arcane, and I think I can't do useful justice to it without having essentially absorbed my entire 2-hour session and then some, and even that would be the case that if I was quite ruthless at shutting those people up, I suspect. So, in terms of the kind of moves that are made to think about probability, you can think about it in a kind of a negative and a positive way of thinking. So the negative way of thinking just says something like the following. There isn't a positive story to tell, or maybe there isn't a positive story to tell about why these numbers count as probabilities, but that's just generally the way it goes. We are in general not in a position in physics of understanding why the number of probability is a conceptually mysterious or puzzling issue to have in play. So absent some knockdown argument, some of which have been offered, absent some kind of knockdown argument that says this can possibly be probability, or can be relatively unmoved by a concern that one doesn't have a positive story. I mean, I shan't defend that any more than simply putting it out there. As a sociological observation, I found, there was a point about 5 or 6 years ago where I was giving a lot of talks to physics audiences as well as philosophy about solving the probability problem in the Everett interpretation. And I found a lot of conversations I had with physicists that it took quite a lot of work to get physicists to accept there was a probability problem in the first place. And for a while I kind of honed the methods of trying to persuade people to explain to physicists why there was a problem. And then I kind of, as a combination, I slightly started to lose my own confidence in that. And I also thought that, what I want to do here, having done this, is to explain to them why there isn't a problem after all. And there's a quicker way to achieve this goal.
What was the reason the physicists didn't think there was a problem?
I don't really know how to answer them not think there was a problem. It's just they weren't particularly responsive to the suggestion there was a problem. These things satisfy the probability calculus. We've got a complicated, developed hard-won story as to why, what do you want. If you think it's a positive problem, then there's a whole bunch of strategies that people have played with. And And I'm not going to go through those strategies in any great detail, except just to say that there's quite a lot, at least at the formal level, of parallelism between strategies that have been played out in thinking about classical probability and strategies that have been played out thinking about probability in Everett. There's also been a lot of controversy about whether the parallels go through, but there's been that kind of, there's a lot of kind of formal structural similarity going on. I don't talk about structure all the time, it's a meta version of it. So for instance, there's a whole bunch of work about understanding probability in Everett, either in terms of long-run relative frequencies or in terms of relative frequencies from an actual infinity of measurements. There are a lot of worries that those moves the question being more circular. There are some quite natural mappings of those objections over to very standard philosophical objections to frequency-based approaches in classical probability theory. We've seen discussions of something like a preclusion principle, or is it called it? The principle, Shelley?
Sorkin does talk about it.
No, I was thinking, what was the principle you...
Cournot's
Cournot's
principle.
yeah, so of that kind of strategy. And then there are parallel moves of that kind in the Everett interpretation. I think Gerhardt talks about preclusion principles and ideas that somehow are allowed to disregard certain bits and that that's okay as a primitive starting point. Thing I find most interesting, spent a lot of time on, there's a tradition in philosophy, probability in general, to try to derive probability out of symmetry considerations. The parallel moves to that kind in the Everett interpretation to try to look at the symmetry structure of the quantum state and derive the probability rule from it, have been played out. You can see some of these originally in Everett's work, but rather more recent ones were played out with David Deutsch and in tedious detail by me. These arguments often get called decision-theoretic arguments. They have a kind of decision-theoretic skin wrapped around them. And the skin is really there to make sense of the idea that probability can be understood at all in a many worlds framework by virtue of operationalizing it, by virtue of interpreting probabilities as something like betting preferences.
Doesn't Lev introduce symmetry arguments?
Yeah, my list is very far from exhaustive. The idea comes up a whole bunch of times. I think you're right, I think it's something in Lev's work. Although Lev says a lot of different things about probability in different contexts. He also talks about Carey measures and primitive principles and stuff like that, and I'm not quite sure what the stable position he has is. But yeah, so there's a kind of decision-theoretic shell around an argument that is called is basically a symmetry argument. And the degree to which you need decision theory tends to turn on how much you think the problem of probability is that we don't think probability makes sense at all in many worlds context, versus the extent to which we don't understand why the right probability rule is being applied. So that's actually, that's really just my kind of 36,000 feet view of the fact that there is a very large and tangled literature on this that's grown up very quickly in the last few years, except to say that from a cosmology point of view, there's a different and very interesting set of ideas coming out of work by, in particular, Anthony Aguirre and Max Tegmark, looking at the kind of duality between the probabilities you get in a single universe or causal region of the universe from the Everett interpretation versus the probabilities you get in an infinite universe, even independent of the Everett interpretation, by the fact that you simply have repetitions. And you can run this argument either way around. You can either say, well, I don't understand Everett probability, but I do understand kind of spatial infinity probabilities, and so I'll read the Everett probabilities off the spatial infinity ones, or vice versa. So, Matt, your question?
Yeah, I mean, if you can kind of, you've got these things that look a bit like probabilities, and then you run some arguments and they show that kind of like the limit of large numbers of experiments and that sort of thing, and then it doesn't quite work, and people get confused about it. Can you say that's like functionally what a probability is? Like people do get confused about it and they try and think of it as being the limit of a large number of things and that sort of thing.
I guess kind of. I mean, look at it this way. The standard large number route will tend to produce mathematical results of the following form. What we'd like to be able to establish mathematically is that in the long run, relative frequencies approach probabilities. You can't establish that. What you can establish is in the long run, relative frequencies approach probabilities probably. So as a mathematical statement that helps us understand how to measure probability, we have an antecedent understanding of what it is, that's just fine. As an analysis, it's in danger of being circular. And people can kind of finesse and fudge their way out of circularity. In the Everett interpretation, you'd like to say, to show that in the limit, relative frequencies approach multiple amplitude, approach branch weights. What you actually find is relative frequencies approach relative branch weights with high weight. And you've got the same circularity concern, and again, you can try to fudge and finesse that. My own feeling about this is the fudges and finesses are pretty hopeless, both in the classical frequency case and the Everett case, but there's a kind of parallel in play there. Okay, so coming back to this issue of structure, I think in some ways that plays closer to some of the issues that have come up so far here and like to come up again. The kind of structural new, let me back off. Here are two rather different takes you might have on the relation between higher and lower level theories in physics or in science more generally. One take, or perhaps I should say, one take is how I should get the manifest image from the details of science. And one take would be the kind of take that Shelley talked about, the kind of take that Tim talked about, a need to get local variables out of your theory. Once you've got them, by all means, do high-level structural functional stuff with them, but ultimately you want them out. And another take, which is certainly vaguer in the way it's put and significantly more permissive, is just to say, okay, all I need to do is say, provided I can show that the high-level structure is instantiated with the low-level structure, I'm done. And there are different kind of worries you would have about that second move. One of them is to worry about what we mean by structure. Tim raised this, I'll come back to it. One is to say, well, just because you've got that structural isomorphism, how is that enough? Why is it that it follows from that's going to get you a covered world? It's, to be honest, quite difficult to make, on that second one, it's quite difficult to make direct progress there. To some extent, you're dealing with very general philosophy of science and very basic, almost intuition disagreements, I guess. In defense of this way of saying things, I'll give a rather indirect defense, which is that I think you can make a reasonable case that the way in which physics in general plays with theory interrelations is that physics is just very generally committed to the idea that to go from theory A to theory B, it suffices to find an isomorphism or an isomorphism in the right domain or something. Now, it's legitimate here to say, well, yes, that is what physics does, and that's what's been wrong with physics over many years. And that's a legitimate move to make in this context. And so to some extent, it almost comes down to to what extent do you see a project as a relatively naturalist, relatively conservative? How do we make sense of these things with minimal, taking as much as we can manage without incoherence of our framework of thinking of it for physics, and to what extent we're more relaxed about saying that this is a wrong turn, bad things have been done here. But I think this issue is significantly more general in the Everett interpretation, and it's likely to come up more in other parts of this conference. Who's familiar with the ADS-CFT conjecture? So I'm not really, so this will be a very vague comment, but we have a very celebrated result in string theory which shows a mathematical isomorphism between two theories which look wildly different. One of them is it's the CFT side, one of them is field theories on a flat space-time without which doesn't have any dynamical curvature. One of them is string theory on space-time that's asymptotically flat but has a whole bunch of geometric goings on and potentially superpositions of geometric goings on happening in it. And as far as I can tell as a kind of observer of the process and having conversations with various people, physics is completely relaxed about the fact that given the mathematical isomorphism between these, we can see these as two very different ways of describing what's ultimately the same underlying goings on. And I think plenty of people in philosophy, but not me, plenty of people in philosophy are legitimately get the concern that, hang on a second, sure there might be a mathematical isomorphism, but if you want a description of what the world is like, it's not okay to say that these two pictures are related. So I think the question of whether physics is entitled to run with this very relaxed structural isomorphism, a map between the two mathematical models that preserves their structure, is all you need. that question goes well beyond the Everett interpretation and feeds into a lot of different general issues that flow through, particularly contemporary fundamental physics.
May I make just a minor comment? So I totally agree with you.
That's a great comment.
What you, what?
That's a great comment.
I think it's a really important question to recognize there's such a thing. Everything can be a little vague. In structural, some kind of structural isomorphism between theories. And that's something else that I would call physical isomorphism between theories. Allow for the possibilities that these are not exactly the same thing, and ask the question, under what circumstances, what do you need for them to be the same thing? Now, you agree with that?
I think that's a good way to phrase the question. I mean, my what else do you need is probably precious little. But yeah, I think that
one
way
would
of phrasing
disagree on how maybe somebody would think you don't need anything more. But I think that would be something to be clear about at the very beginning. I mean, and if somebody has the really strong view that you definitely don't need more, that's something. I don't know, is anybody like that?
I flirt with it.
Okay.
So yeah, I mean, let me pretty much stop there and throw it open actually. So I mean, that's how the Everett interpretation works. It starts with or how it works from this extremely anachronistic model perspective. It starts from the realization that we've moved a very long way on from our grip of measurement processes and the macro divide that we had in Copenhagen. We know mathematically structurally how to use unitary quantum mechanics to get out something which has the structure of a branching reality where the branch weights match the probabilities. It then says, can we just take that literally as a description of the world? To do so, it requires committing itself to a thesis about structural isomorphism being enough to recover the macro world, which is controversial in philosophy, but plain. It's kind of standardly played with all over various other bits of physics. It also relies on either being able to take the same take on probability, or being able to run a kind of play on or Houns's line on probability, or being able to say something positive and new about probability. If you can do those things, it has the enormous virtue of complacency. In a meeting a couple of years ago at the Foundations of Quantum Mechanics, there were lots of talks about quantum information and how we had to really think about all these issues and understand the change in our worldview that came from quantum mechanics. I said something like, the purpose of looking at the interpretation of quantum mechanics is to wake us from our dogmatic slumber. And the point of the Everett interpretation is to help us get back to sleep again. There's a kind of sense in which this is a very profligate, very radical position, certainly radical vis-a-vis our common sense picture of the world. There's a funny sense in which it aspires to be extremely conservative. It's conservative about philosophy in the same way that's been a common cause in this week. It's conservative in the sense that it doesn't reject the idea that physics should be in the business of giving a mind-independent, objective description of something that could pass property for the universe as a whole. It's conservative at the level of physics by just saying, give me a quantum theory and I'll run with it. It's not committed to any given kind of modification or change. In a sense, that's boring, but it does have the virtue that if you can make it work, it lets you carry on with the quantum mechanics we have, but while having a clear way to understand what to do. Okay, let me stop there and just throw it open to any questions. Yeah, David.
So I'm going back to about 3/4 of the way through your talk, where you wanted to claim that that on the kind of view you were putting up there, all of the probabilities of sort of standardly identifiable macroevolution, like thermodynamic evolution or something like that, were going to turn out to be quantum probabilities.
Yeah.
So I'm just trying to see how this works in a specific case.
Okay.
Take a box with a gas,
Yeah.
okay, and get the walls of the box out of the physical system. Let them just be represented by sharp, by potentials that go fairly sharply to infinity. Along certain planes.
Yeah.
Okay. Then, in order to believe what you're saying, I'm going to need to believe something like this. That there are literally zero quantum, so consider a macro state where the gas is initially confined to one corner of the box. Suppose that there's even one wave function compatible with that macro state. That has the property that 10 minutes from now, or whatever the appropriate relaxation time is, that wave function, the evolved wave function, has no support outside of the equilibrium region. If there's even one state like that, then the probabilities of evolving backwards out of the equilibrium region, right, are not going to be quantum probabilities. They're going to be probabilities that are going to come from a sum over initial positions. Now, it doesn't seem implausible at all, given how much space the equilibrium region takes up, okay, that there's going to be at least one wave function compatible with the initial condensed macro state, excuse me, that's going to evolve 10 minutes down the road into a wave function whose support outside of the equilibrium region is zero. Or am I missing something?
Well, I can't give you an argument as to why that won't happen, but I think the burden of proof has a rather different structure. I mean, notice in the classical case, we can prove there are such things.
Right.
In the quantum case, it's just a thought that there's loads of dynamics going on.
Right.
There's what going on?
Well, in the classical case,
loads of dynamics going on.
I mean, the way we prove there are such things is just because everything ends up somewhere.
Right,
You know, in some particular, so some of them end up in the equilibrium.
Yeah, but I mean, quantum mechanically, what you'd expect to find, I think, is that if I take a generic state confined to half the box.
In a generic state.
Yeah, I know. But just,
I'm sure that it's the case that in a generic
yeah, but I want to
state,
fill in the
there'll be
details.
some leakage outside.
I want to fit into the details of generic states. I think what the generic state would do, I take it, is evolve to a superposition of not having left the box and having left the box, and be overwhelmingly in the not having left the box. Sorry,
Wait,
having left the
I
box.
don't mean left the box.
No, sorry, left the left hand
Even
side.
when it's confined to the box.
Yeah, I misspoke. Left the left hand side of the box. I
Yeah,
misspoke. So the point is, when we know there are fluctuations, I was just thinking that the gases takes a little work to get the framework because it's not transparently a probabilistic system in the first place. But of course, the probabilities we're after are the low probability of the system finding its way of the system, the low but non-zero probability of the system just doesn't bother leaving the left-hand side half. So I'm pretty sure those, for generic states, those probabilities are going to come out from quantum mechanical phenomena, but you're worried there could be some kooky state. Well, there might be, I don't know. It's just that we have dynamical arguments that seem to be fairly generic for states.
If you don't take into account the environment of the box, if you just
Right.
focus on, then of course by time reversal you're going to have,
No, it's not, of course.
yeah,
Because time reversal
It
is...
could be that it could be,
yeah,
and I think David is depending on this being the case,
go ahead.
that every single wave function, every single microscopic wave function compatible with the initial condensed macro state, okay, evolves into a superposition of being in equilibrium and being out of it.
Yeah, or being...
There's nothing that makes it obvious that that's false.
For a typical behavior of a gas in a box,
Yeah.
typical, there's nothing too funny like that. If without decoherence and those effects, you're going to certainly have the time reversal thing, things are going to go bad. You're going to need to appeal to a typical equilibrium macro state, staying in equilibrium. So
Yeah, so if that turned out to be true, I could live with it, but that doesn't follow from the framework.
Yeah, no.
Think about the decaying atom case
David's
again.
denying that.
The time reverse is going to take a very carefully arranged superposition
Right.
of
Equilibrium.
Of
and
equilibrium.
non-equilibrium.
but it's just if you think about that, you might get that impression. But just analyze. Various people have done this. Analyze the simplified behavior of a gas in a box. It's a finite dimensional system. You fix the initial energy. You look at non-equilibrium macro state, macro wave functions corresponding to non-equilibrium macro states. Look how they evolve. Ask how equilibrium states are going to evolve. That's an easy analysis to do, and it's pretty clear.
Presuming it's easy because we've got what we're doing.
Because you could explicitly solve Schrodinger's equation in terms of the energy eigenstates. It's easy to get it's much easier to get a handle on the dynamics and quantum mechanics.
But you've turned off the interparticle scattering?
No, you definitely, all you need to do, because you just decompose the wave function into energy eigenstates. You have an explicit solution. In terms of the energy eigenstates, you get a really good handle on lots of stuff that's happening if you ignore all interactions with the environment.
Okay. So I'm not entirely sure I follow that. It sounds like we should have an offline chat about it. I guess that, there's a backup comment which would be, I don't mind falling back on the, well, don't ignore the actual environment necessarily, but sure, we should have a chat about that. Yeah.
It seems like there's a common thread through classical mechanics and the relationship between frequency and probability and justification for ignoring low branch weights and Everett that tells us that we need sort of a meta measure theory that tells us which measures are the right ones to use.
Well, I guess I'm saying no. We do need we need a principle that tells us which measures to use. Well, maybe we do in classical physics. Maybe the principle is simply that says use this one, but we need a principle there in quantum physics. This is partly what the debate we're having here concerns, but it's a prima facie plausible that you don't need a measure call like that. You'll still need this. This is where we might need a typicality requirement of some sort. It's still the case that there are going to be states that aren't any good, but it's not clear that one needs a measure-based way of picking them up. And of course, the measure, I don't need to add a measure rule in quantum mechanics to get the probability distributions out because I'm getting it straight from the quantum theory. In Everett, I'm getting it directly, insofar as Everett works, in modification, in alternative strategies, I'm getting it via some other machinery that plugs into the quantum amplitudes. But either way, I'm getting it out of the quantum mechanics. So I haven't. This is a moving part that is present in the classical version and not the quantum version.
The typicality concern would be something like this rule over which class of measures are good enough.
I'm not sure I'm saying that.
Well, I guess in another sense, it seems like if you want the buck to stop and not to have a meta theory of which measures to use and then another meta theory of what measures to use on another level, you need a connection to the empirical world.
Yeah, I'm just not clear where this measure requirement is coming from. The measuring in quantum theory is just multiple amplitude that's given to us. It's the worry that you need a measure to make sense of the notion of typicality.
Yes, and the question of long-term relative frequencies, you want them to approach probabilities, but you can only show that happens probably, and that if you want to be able to ignore the certain branches, you have to, as the Everett case, you have to argue that they have low branch weights. What is the justification for ignoring those? For saying those branch weights are low, you need a different kind of measuring.
No, wait. The justification for saying the branch weights are low is a theorem. It's about you might have a question as to why you're allowed to ignore low branch weight branches, but the fact that those branches have low branch weight is just calculation. It's just the law of large numbers.
So, I guess that the problem here is the different understandings of the word weights. You mean the ones that come up in quantum mechanics, and you mean the ones that are relevant.
Yes.
It's very important to bear in mind that there are a lot of analogies and similarities between the kind of multiverse you get out of Everett, so type 3 multiverse if you like, and the kind of multiverse you get out of other stories. But there's a very important disanalogy, which Ted might perhaps understress as much as he could do, which is that the Everettian multiverse comes with a measure built in. It's not that we have to have a further conversation about what the measure should be. It's built into the theory. There's a serious philosophical question about why we're justified in using that measure in the way we use it. But insofar as that can't be satisfactorily answered, then the theory is in trouble. It's not that you could peaceably use a different one. Yeah, David.
David, it seemed like you were saying something just now that contradicted something you were saying earlier.
I am large, I contain multitudes.
And it seems like the thing you were saying earlier is what seems right as far as I can understand. What you were saying just now. So here's the situation that I thought was established earlier. Even if one puts aside, say, the worries associated with the box of gas I just raised, even if one were to grant that all of the probabilities of different recognizable macroevolutions come right out of the quantum amplitude, okay, it's still going to be the case that associated with the initial macro state, there'll be some states which give you recognizable macroevolutions of one kind or another,
Yeah.
or superpositions over them.
Yeah,
And there'll be some other states that give you mush,
exactly.
like you were saying, okay? The business of neglecting the mush ones,
Yeah,
even putting aside the worries I just raised,
yeah.
the business of neglecting the mush ones, you know, in your language, requires what you were just calling additional moving parts.
Agreed. That's right.
Okay.
That's correct. And one way you could do that is a typicality route, and that potentially has a measure issue.
Right.
But it's not clear that's the only route you can have.
Right.
That's exactly what I was trying to say. I think you're just saying it better.
Yeah, but notice that the need to have a typicality route there is not the only move you might want to make. That's just what Jen was suggesting.
Yes, sure.
So I'm still really confused about the ontology. You know, we're supposed to think of the many worlds as one wave function with many different other states that we're pushing among. So we're supposed to think of that as, in some sense, the real world.
Okay, so two comments there. I mean, one's just a quick, for clarity comment. I mean, sometimes one hedges these things. So to be completely clear, the theory does entail that there are many worlds and they're just like ours. So the macro-ontology is definitely an ontology of many, many worlds. I've kind of dodged the questions, or blanked the questions so far, of what the micro-ontology is. I think thinking about it as the wave function is a misleading way to think about it. And my reason for saying that is something like this. It's kind of committing a not entirely, it's not an insane thing to think, but I think it's committing the same kind of error we'd be committing if we looked at classical mechanics and said the world is a phase-space point. I think the wave function, the nature of the state space is that points in the space are supposed to represent physical goings-on, and the space itself is extremely highly structured so as to keep the structure required in the state space down to nil. The wave function is a kind of hybrid object of that kind. It's got plenty of structure, but a great deal of its structure is implicitly represented in the very high level structure on the quote configuration space on which it sits. So I think if we wanted to tell the micro-ontology of the Everett interpretation, looking at the wave function is probably the wrong way to go. What's the actual ontology? Well, I won't give you a general answer because I think it's like asking the question, what's the actual ontology of classical mechanics? The answer is going to depend which classical theory you have in mind. And the ontology of general relativity is very different from the ontology of one harmonic oscillator. The ontology, I could give you a couple of different accounts available for what the ontology of quantum field theory looks like in the Everett interpretation, for instance, but there are various different ways of setting it up. I don't necessarily have a firm favourite.
What about just for non-relativistic quantum mechanics?
Not entirely sure, I would say. I'm relaxed about saying I know what to say about QFT and I'm not sure what to say about non-relativistic quantum mechanics because I'm happy to make it parasitic on the QFT answer. One strategy I'd run if I want to think of the micro-ontology of non-relativistic quantum mechanics is to throw it into the Fox-based formalism and think about number operators as operator value functions in space-time, and then think about the states defined for those regions. So the kind of ontology you get from that, as with the ontology you get from quantum field theory, is an ontology, well, in Shelley's terminology, of beables that mostly aren't local. It's to do with, space-time regions have properties, but the properties of composite regions do not supervene on the properties of their component regions because of entanglement.
That was kind of what I was going to be asking, but I did want to throw in that you brought up ADS CFT, and a lot of those people make use of Everett in various ways, universal wave function and stuff. And you said it was relaxed isomorphism, and just from Everett's point of view, he actually called it a homomorphism, and that's where he got the term of empirically faithful, because it was homomorphic to our world. That he didn't make the claim necessarily that it was empirically adequate, which would have been all the worlds. Do you have some thoughts about the empirical adequacy of the theory as you now understand it?
I think it's a bit clear. I couldn't really defend it. I'm not quite sure I get the question. I mean, what was the
Is it useful?
That's a very different question, but yeah, okay, it's useful in the following straightforward sense. It lets you, insofar as you buy it lets you make sense of what people are doing in quantum physics all over the place, including in string theory, in QFT, in whatever. It lets you make sense of their practice in a relatively conservative way, but without needing to require perhaps one set is useful. It gives you a clear way to understand unity quantum mechanics. If there is a clear way to understand unity quantum mechanics, that's highly desirable given the empirical fruitfulness of unity quantum mechanics. If we can't understand unity quantum mechanics coherently, then perhaps we have no choice but to modify it. But nice to hold that.
Without getting too much in it, can you say a little bit about the sort of decision theoretic shell that would go around kind of symmetry arguments? Give me a problem. I mean, at least sort of whether you think it's sort of essential or just kind of to fulfill some people's requirements.
Okay. All right. So here's the sentence which is not essential. If you were to grant me that it makes sense to allocate to Everettian branches probabilities which obey the probability calculus, and you also were to grant me that those probabilities should supervene on the quantum state itself, never mind why those things should be true. If you grant me that stuff, then I can derive for you the Born rule without any appeal decision doing. So that's a sense which is essential.
We got to given your take on the situation. I mean, is it likely that other arguments are going to be sufficient to do that, or is likely place?
I think it's very depends on the starting point. I mean, the name of the game because there are so many people who have so many very different problems from Everett that you end up with different responses tailored to different audiences. What do I think? Well, I guess, I mean, if I had to say what's the best way of understanding it, then I think symmetry-based decision theory is lost ways are the best way I know to understand it. Having said which, I don't particularly mind being pluralist. I mean, it wouldn't entirely surprise me if one time there were multiple routes and the controversies about which was the best way to get it started to mirror controversies in classical probability. Craig says,
I thought that the low-dimensional space was coming out as what, part of what emerged, like the cat. But now what you've just described sounds like it's in there at the bottom. So how am I to think about that? So it seems very crowded there at the bottom.
Yeah.
And then how do I think of the functional specification of the cat? So now, if I put it in the spatial, so do I say the whiskers are an inch apart or something? Is that part of I specify what cat is functional? I'm inheriting it's about stuff in a. I don't know how to put this. Just the first part then.
Okay. Well, I mean, to say something quick about the second part, and I've got it. I think in practice, the things that you're instantiating structurally and openly, I say things like cats are going to be big chunks of various interacting bits and pieces. In terms of the first thing, well, again, where space-time fits into the theory is going to depend on which quantum theory you have in mind, because the way space-time fits into quantum theories is theory dependent. In QFT, space-time enters the theory fundamentally as a baseline point, as in via the map from space-time points to field operators. So that's in the theory, so it's in Everett. On what I find the most conspicuous way of thinking about the ontology, then the micro-ontology at the baseline level is a lot of, it's a quantum state for every spatial region, many of them are entangled. The entanglement structure, because of decoherence, ends up being very layered. Relative to each of those layers evolves in a dynamically isolated way from the other layers, and you get in this kind of way. Within each given layer, you've got the kind of structures that pick up, cat goes on. All this stuff is coexisting in the same space-time. A nice metaphor, I mean, people in cosmology can remind me where this has got to. There was a time a while ago where people talked about shadow matter that would interact. I mean, some of dark matter is a little bit like this, but shadow matter that could make cohesive things like stars and planets, but which would interact, which would basically not much interact with stuff in our bit of reality except through, in that case, except through gravity. So as a metaphor, you can think about the other branches of Delta as shadow matter branches. And of course, it's then just a terminological issue as to who's the shadow and who isn't.
Okay, so then there are all these other Craigs sitting right here.
Well,
but I'm just not.
Insofar as QFT is exactly true. If you ask me what's the location of the other ones, given QFT, that's the right answer. If you say what's the actual location, I don't know because I don't know how quantum gravity would go out. But my suspicion, there are very strong reasons to think that the gravitational degrees of freedom are going to get entangled with matter degrees of freedom, And so I think those other trades are going to be entangled with their own gravitational surroundings. Because gravity is manifests as a curvature of space in GR, then I think the right mathematical framework for making sense of this would actually be the superposition of spaces with different grades in different spaces. I don't have to set that mathematically. If I did, it would make it very difficult. David, how long should I be taking questions for?
Oh,
I'm fine, but...
I should say just enough time to allow me to ask.
Okay, well, you're next but one, I think, in terms of my attempt to keep track.
We should stop in 5 minutes.
Okay, let's do 5 minutes then. Fine. So Chris.
Yeah, I was just worried about what might be metaphysical implications to the ontology of the theory, right? At the macroscopic level.
Yeah.
So you've got worlds, you've got copies of individuals, and I'm curious about the sort of like nature of the relationship between these copies. In other words, are you going to inherit some of the worries the modal realist has about individuals that were indiscernibility of identity kinds of worries? And if so, if that's true, if we've got the implication right, what's the solution? Is it something like counterpart theory?
Well, okay. So as far as individuals in different worlds are concerned, so the modal, the modal realist wants to be using the different worlds in the framework as a grounding of counterfactual thought. And so I need somehow to ground claims like, if I had prepared my lecture better, it would have been higher quality, by saying that, by saying that somehow that's, the truth maker of that is the alternate branch, the alternate possible world in which somehow, quote, I prepared it better. And now we have a problem about whether that's really me or whether it's simply a counterpart to me. And to make the wheels of the modal realist analysis of counterfactual work, I need to answer questions like that. So I have no interest. There are people, and Alan Wilson has a serious desire to make these things work, and they need to have something to say here. I have no interest in using the Everettian branching structure to do philosophical work like ground counterfactuals. So I have no problem with just saying, well, there's another version of me there, and make it a semantic question whether you want to say it's me or a version of me.
I see. Okay, so I understood that there were different motivations for modal realism or realism and just quantum mechanics. I was just still really curious about the nature of the relationship between these copies. I mean, you do have these copies, and so there should be some reflection upon what is metaphysical nature, what the metaphysical nature of the relationship here is. Right? And you're saying, well, I'm not sure if I'm clear on your answer. You just don't.
Qua philosophy of physics, I don't much care. I think there's an interesting metaphysical question to answer there, but I don't myself have very much to say on it.
Is it a metaphysical question or a semantic question?
Well, that itself could be a question you could ask. Yeah, there are coherent questions here, and I thought a little bit about the semantics of how these things are set up, and you can. To say just a little bit about it, you can tell different stories about what the correct semantics is of discourse given a many worlds framework. There are semantics that you can tell that are fairly radical, and there are semantics that are pretty conservative. My kind of meta philosophy of language considerations lead me to think that the rules for what the correct theory of meaning is basically are largely tied to fealty to use. So my feeling is that the conservative choices are the better ways to go. There's still some underdetermination there, which I'm kind of inclined to just write off the kind of Quinian indeterminacy, at the risk of the kind of thing gets stereotyped here. This is something that I now have thought about for a while, but there's one of the chapters in my book talks about it, so buy it.
Do you think there is work to be done here?
Yeah, there is work to be done. I don't think it's work. I think my own view is it's work where we have a sufficiently good idea that nothing goes catastrophically wrong, but it's not a reason to affect how we interpret the extent of physics. But I think there's a whole bunch of really interesting metaphysical questions to ask. And I think, in some ways, I think simply as a strategy, it can be more fruitful to take the Everett interpretation as a starting point and then ask how various metaphysical questions are answered there, whereas what a lot of literature tends to do is more taking its metaphysical starting point as fixed and use that to try to see what's wrong with the Everett interpretation. So there are just different routes how one can play out that story. David, you can
Just about the answer you gave, say, just in the field theoretic case, to the question of fundamental ontology. here's what puzzles me. So you have a state, as it were, or a physical situation associated with every region.
Yeah.
Okay? So these various, well, I don't know what the right word to use is. These various conditions, as a purely logical matter, can't be varied independently of one another. That is, the ones with the situation of a region determines the situation of all the subregions within that region. Okay, so there's so these various components of the situation of the world aren't logical components in the sense that it's logically possible to vary them
while holding them,
independently of one another. And also, all of them follow from the state of the bigger region. So why wouldn't the right thing to say to oneself be the state of everything there is to say about the world is the state of the biggest region? That is the state of the whole thing. And that's the end of the story.
I don't mind saying that, but I think simply saying that you haven't told me enough about what that thing is like and what its features and properties are.
It's a wave function.
Well, that's fine if the way you want to. Okay, that would be fine if you're happy to help yourself to configuration space and interpret it that way. I don't particularly want to dump a third basis in there, and I want to know how to represent in the theory the objective facts about space, about how these things relate to spaces. I mean, here's a way of telling the story you're telling. This is more kind of traditionally metaphysical than I normally talk. This links a little bit to kind of some of the way Jonathan Schaffer talks about these things. But if you want, you could say the following: there's one thing, the quantum field. It has a number of properties. One of its property is that it has this value in the space-time region. Another of its properties is this. These are not logically independent properties, and they link together in certain ways.
But compare that to compare that to how it would look in the analogy we're drawing to classical mechanics between many particles in free space and a point in phase space. There, in the free space case, you really have a state associated, like you were saying, go with a kind of Fock space representation. Each region either does or doesn't contain a particle of a certain type with a certain momentum, or each region of a six-dimensional space either does or doesn't contain a particle. These are logically independent of one another. There isn't any of the kind of stuff that's going on in the quantum mechanical version. That you might want to say, that's why, in the classical case, it would be silly to represent things in a serious ontological way as a point in phase space. And the reason it's not silly in quantum mechanics is precisely because of the unavailability.
No, I see the pressure of that, and I certainly there's a large there. But the major problem I have, the most severe problem I have of doing the kind of configuration space run you want to do there is largely silent in an relativistic particle mechanics case. It's a lot to do with the degree to which that framework messes with the relativistic invariance to a large extent, and also the extent to which it picks out a certain field configuration basis. So I think one of the issues about field theory is we can be really quite profligate in changing the field we have in mind. So I think having a story which, this is a matter of way of algebra, having a story which respects the internal space-time symmetries of the theory has a higher priority to me than a theory that gets the metaphysics in a simple, clean way. I think I've now used up your 5 minutes plus some, so maybe I better stop there.